A sharply defined line stretches across the rolling terrain of the southern Appalachian Mountains, visible from above as a remarkably straight scar that cuts through a region otherwise known for its irregular ridges and winding valleys. It runs for nearly 500 miles, or about 800 kilometers, crossing multiple states with a consistency that immediately raises questions. Why does this line remain so straight in a landscape shaped by folding, uplift, and erosion? What force could have carved such a persistent feature through terrain formed over hundreds of millions of years? And why does this ancient structure still leave such a visible imprint on the land today, long after its original movement has ceased? This feature, known as the Brevard Fault Zone, reveals itself most clearly when viewed from elevated terrain or satellite imagery, where the contrast becomes unmistakable. In a region where mountain ridges typically curve and twist, the fault stands apart as a linear boundary, marking a zone where the Earth's crust once fractured and shifted on a massive scale. Its presence is not subtle. Instead, it appears as a long, continuous corridor where valleys align, rivers follow a common path, and the landscape itself seems guided by an invisible line drawn deep within the crust. The fault begins in northern Alabama, extending northeastward for hundreds of miles. It passes northwest of Atlanta, continues through western North Carolina along the base of the Blue Ridge, and reaches into Virginia, where it blends into related geological structures. Though its name changes in some areas, the underlying feature remains part of a single, continuous system. This continuity is part of what makes it so striking. Geological features often fragment or fade over distance, yet this one maintains a recognizable form across a vast stretch of terrain. The reason for its visibility lies not in current movement, but in its legacy. The Brevard Fault Zone is not actively shifting in the present day. Instead, it represents a zone of weakness formed during ancient tectonic activity. Over immense spans of time, forces within the Earth caused large blocks of crust to move past one another along this boundary. These movements fractured the rock, breaking it into smaller, more easily weathered pieces. While surrounding rock remained relatively resistant, the material within the fault zone became more vulnerable to erosion. As water, wind, and temperature changes acted on the landscape, this weakened zone began to erode more rapidly than its surroundings. Rivers and streams preferentially carved their paths along this line, deepening valleys and reinforcing the linear feature. What appears today as a scar is, in reality, the cumulative result of millions of years of erosion acting on a pre-existing zone of structural weakness. Topographic maps make this distinction even clearer. The fault zone often corresponds to lower elevations compared to adjacent ridges. In some areas, it forms a natural corridor through otherwise rugged terrain. Roads and transportation routes have, in many cases, followed this path, taking advantage of the easier passage it provides. This alignment between human infrastructure and geological structure is not coincidental. It reflects the enduring influence of the fault on the shape of the land. Beneath the surface, the story becomes even more complex. The rocks within the Brevard Fault Zone differ significantly from those on either side. Thinly layered, mineral-rich formations dominate the zone, including rocks with high concentrations of mica. These minerals contribute to the rock's relatively soft and flaky nature, making it more susceptible to breakdown. In contrast, the surrounding regions often consist of more resistant rock types that form higher ridges and steeper slopes. This contrast creates a visible boundary in the landscape. On one side, mountains may appear more block-like, with broader, flatter features. On the other, ridges may be tightly folded and sharply defined. These differences are not random. They reflect the underlying geological history of how the rocks were formed, deformed, and transported over time. During the formation of the Appalachian Mountains, the region experienced multiple episodes of tectonic collision. Continental masses converged, compressing and uplifting the crust. Rocks that were once buried miles beneath the surface, at depths of several miles or several kilometers, were pushed upward and exposed. The Brevard Fault Zone played a role in this process, acting as a boundary along which rocks could move and shift. Movement along the fault was not a single event, but occurred in stages, with periods of activity separated by long intervals of relative stability. Each episode left its mark, creating a layered history recorded in the rocks themselves. In some cases, fragments of rock were transported considerable distances along the fault, resulting in unusual combinations of rock types appearing side by side. One notable example occurs near Fletcher, North Carolina, where a marble quarry lies directly within the fault zone. Marble is not commonly found in this part of the Appalachian region, making its presence here particularly significant. Its location within the fault suggests that it may have been transported from elsewhere during one of the fault's active periods. This kind of displacement highlights the scale of movement that can occur along major fault systems. Geologic mapping further illustrates these patterns. By assigning colors to different rock types, maps reveal how certain materials are concentrated along the fault zone. These visual representations help to clarify the relationship between the fault and the surrounding landscape, showing how geological processes have shaped both the composition and the topography of the region. Above ground, the effects of these processes are evident in the contrasting styles of the mountains. Southeast of the fault, the terrain often appears more uniform, with broader, plateau-like features. Northwest of the fault, the landscape becomes more intricate, with ridges that branch and intersect in complex patterns. These differences reflect variations in how the rocks were folded and deformed during the mountain-building events. In some areas, the rocks form structures that resemble tightly compressed folds, similar to the bellows of an accordion. These folds indicate intense pressure forces that compress the rocks and force them into layered patterns. In other areas, the folds are tilted, creating flatter-appearing surfaces that contrast with the more sharply defined ridges nearby. The fault zone marks the boundary between these different structural styles, acting as a dividing line in both composition and form. The orientation of the fault adds another layer of complexity. It tilts toward the southeast, suggesting that the movements along it were not purely horizontal. Instead, they involved a combination of horizontal and vertical displacement. This combination contributed to the intricate arrangement of rocks seen today, where layers have been shifted, stacked, and sometimes overturned. Despite its scale and visibility, the Brevard Fault Zone does not extend deeply into the Earth's crust in its current form. The processes that created it were tied to ancient continental collisions that have long since ceased. Beneath the fault, the rocks are thought to mirror formations found farther west, indicating that the current arrangement is the result of large-scale movement and reorganization of the crust. This idea is supported by the concept of crustal stacking, where layers of rock are pushed over one another during tectonic compression. Visualizing this process helps explain how the Appalachians may have once reached much greater heights than they do today. Some interpretations suggest that the region could have rivaled modern high mountain ranges in elevation before erosion reduced it to its present form. Evidence for deep crustal movement is also found southeast of the fault zone, where rocks show signs of having been squeezed and pushed outward. This behavior is consistent with the idea of a channel within the crust, where material flowed under pressure and was later exposed at the surface. Such features provide insight into the dynamic processes that shape the mountains, revealing a history that extends far beyond what is visible today. Traveling along the path of the Brevard Fault Zone offers a direct encounter with these geological features. In areas northeast of Hendersonville and near Old Fort along Interstate 40, the changes in terrain become particularly noticeable. Valleys align with the fault, slopes shift in character, and rock exposures reveal the layered structures formed deep underground. These observations provide a tangible connection to processes that occurred hundreds of millions of years ago. The persistence of this linear feature across such a vast distance continues to draw attention, It stands as a reminder that the landscape is not solely defined by elevation or surface appearance, but by the underlying structure and history of the Earth's crust. Each ridge, valley, and rock formation along the fault zone reflects a sequence of events that shaped the region over immense spans of time. Even in its current inactive state, the Brevard Fault Zone influences the environment in subtle but significant ways. Water drainage patterns, soil composition, and vegetation can all be affected by the underlying geology. These factors, in turn, influence how the land is used, from agriculture to transportation. The fault's legacy extends beyond its geological origins, shaping the interaction between people and the landscape. As attention continues to focus on this feature, its scale and clarity remain central points of interest. A nearly 500-mile line, or about 800 kilometers, cutting across one of the most studied mountain ranges in the world, is not easily overlooked. Its presence invites further examination of how such structures form, evolve, and persist over time, raising broader questions about the forces that shape the Earth's surface and the hidden patterns that lie beneath it. Farther along its northeastward path, the same linear signature continues to guide the shape of the land in ways that are not always immediately obvious from ground level, but become unmistakable when viewed across larger distances. The valleys that align with the Brevard Fault Zone are not isolated features. They form a connected system that reflects the underlying weakness in the crust, a weakness that has persisted through vast stretches of geological time. Rivers occupy these corridors because the fractured rock offers less resistance, allowing water to carve deeper channels compared to the surrounding terrain. Over millions of years, this preferential erosion has amplified the original structure, transforming what began as a zone of displacement into a defining element of the regional landscape. In several segments of its length, the fault zone influences drainage patterns in a way that creates long linear river courses that contrast sharply with the more branching and irregular systems found elsewhere in the Appalachians. Streams tend to run parallel to the fault before eventually turning away, creating angular junctions that reflect structural control rather than random development. This pattern reveals how deeply the fault has shaped the hydrology of the region. Even though the tectonic forces that formed the fault have long since subsided, the imprint they left behind continues to guide the movement of water across the surface. The soils that develop along this zone also differ from those found on adjacent ridges. Because the rock within the fault is more easily broken down, it produces finer, more mineral-rich soils. These soils can support different types of vegetation compared to the thinner, rockier soils found on more resistant formations nearby. In some areas, this results in subtle but noticeable shifts in plant communities, with certain species appearing more frequently along the fault corridor. These variations are not random, but are tied directly to the composition of the underlying rock and the way it weathers over time. In addition to influencing natural systems, the Brevard Fault Zone has also played a role in shaping patterns of human activity. Settlements, roads, and transportation routes often follow the easier terrain created by the fault. Navigating the rugged Appalachian landscape can be challenging, and any natural corridor that offers a more gradual path becomes a valuable route. Over time, these paths have been reinforced and expanded, turning geological features into practical infrastructure. Highways that pass through this region frequently align with the valleys carved along the fault, providing a direct link between distant areas that might otherwise be difficult to access. The relationship between the fault and transportation becomes especially apparent in areas where major routes cut through the mountains. These passages often coincide with gaps or lower areas created by erosion along the fault zone. Such gaps are not merely convenient, they are the direct result of the long-term weakening of the rock. Without the presence of the fault, these routes might not exist in their current form, or they would require far more extensive engineering to traverse the terrain. Looking deeper into the structure of the fault zone, the internal arrangement of rocks reveals a history of repeated deformation. Layers that were once horizontal have been tilted, folded, and in some cases stretched or compressed beyond recognition. The presence of shear zones where rocks have been smeared and elongated under stress indicates that movement along the fault involved significant pressure over extended periods. These features are preserved in outcrops along the fault, where careful observation shows the alignment of minerals and the orientation of layers that record the direction and intensity of past movement. The minerals themselves provide additional clues. Mica-rich rocks within the fault zone often display a shimmering appearance due to the alignment of mineral flakes. This alignment is not accidental. It forms as minerals recrystallize under pressure, orienting themselves in response to the forces acting on the rock. The resulting texture not only reflects the conditions under which the rock formed, but also contributes to its mechanical properties, making it more prone to splitting along certain planes. This characteristic further enhances the susceptibility of the rock to weathering, reinforcing the development of the linear valley. In certain locations, the fault zone contains evidence of fluid movement deep within the crust. Minerals that form in the presence of heated water suggest that fluids once circulated through the fractures, depositing material as they moved. These processes can alter the composition of the rock, sometimes concentrating valuable minerals in localized areas. While the Brevard Fault Zone is not widely known for major mineral deposits, the presence of such processes indicates that it shares characteristics with other fault systems where economically significant resources can be found. The broader context of the Appalachian Mountains provides important insight into how the Brevard Fault Zone fits into the larger geological framework. The Appalachians themselves are the result of multiple continental collisions that occurred over hundreds of millions of years. Each collision added layers of complexity, stacking and deforming the crust in ways that produced the mountain range seen today. The Brevard Fault Zone represents one of the many lines along which this deformation was concentrated, serving as a boundary that accommodated movement during these events. At one point in geological history, the mountains in this region were far higher than they are today, potentially reaching elevations comparable to some of the tallest ranges currently on Earth. Over time, erosion wore these mountains down, removing vast amounts of material and exposing deeper levels of the crust. The rocks now visible at the surface were once buried at significant depths, subjected to high temperatures and pressures before being brought upward through a combination of uplift and removal. This long process of uplift and erosion helps explain why the Brevard Fault Zone, despite being an ancient feature, remains so clearly visible. The removal of overlying material has effectively revealed the internal structure of the crust, allowing features that formed deep underground to become part of the surface landscape. In this sense, the fault zone is not just a surface feature, but a window into the past, offering a glimpse of processes that are otherwise hidden from view. Another aspect that draws attention is the way the fault interacts with adjacent geological zones. On one side, the rocks may belong to a different terrain, representing a distinct piece of crust that originated elsewhere before being attached to the continent during tectonic collisions. The fault marks the boundary between these terrains, highlighting the complex assembly of the Appalachian region. This boundary is not merely a line on a map, but a record of ancient movement that brought together pieces of the Earth's crust from different origins. In some areas, the contrast between these terrains is reflected in the physical properties of the landscape. Differences in rock hardness, composition, and structure create variations in slope, elevation, and erosion patterns. The fault zone acts as the dividing line between these characteristics, making it a key feature for understanding the broader geological history of the region. Despite its ancient origins, the Brevard Fault Zone is not entirely without modern relevance. While it is not considered an active fault in the sense of generating frequent or significant earthquakes, it remains a part of the Earth's crust that has been weakened by past activity. In rare cases, minor seismic events can occur along old fault zones, though these are typically small and infrequent. The primary significance of the Brevard Fault Zone today lies not in current movement but in its role as a structural feature that continues to influence the landscape. The study of such features contributes to a broader understanding of how continents evolve over time. By examining the characteristics of the fault zone, including its orientation, composition, and relationship with surrounding structures, it becomes possible to reconstruct the sequence of events that led to its formation. This reconstruction provides insight into the processes that shape not only the Appalachians, but also other mountain ranges around the world. If you found this deep dive into one of the most fascinating geological features in the Appalachian Mountains insightful, make sure to like, share, and subscribe for more detailed breakdowns of the world's most intriguing natural phenomena. And do not forget to tap that hype icon to help this video reach a wider audience.